The universe is expanding faster than previously believed, and dark energy is now looking a little shaky in explaining why the cosmological constant cannot be determined accurately. Something is wrong with our universe. At stake is the standard theory of the cosmos that has reigned since the discovery of dark energy. The theory describes all the visible matter and energy in the universe, along with dark energy and cold dark matter, showing how they evolve according to Albert Einstein's theory of gravity. The theory perfectly captures features of the early universe, patterns best seen in ancient microwaves coming from a critical moment when the cosmos was 380,000 years old. Since the Planck Space Telescope's first map of this cosmic microwave background was released in 2013, scientists have been able to precisely infer a distance scale in the young universe and use it to fast forward from the 380,000 year mark to now, to predict the current rate of cosmic expansion known as the Hubble constant. The Planck team predicts that the universe should expand at a rate of 67.4 kilometers per second per megaparsec. That is, as you look farther into space, space should be receding 67.4 kilometers per second faster for each megaparsec of distance. However, a team of cosmologists led by Professor Adam Rees, a distinguished astronomer at the Space Telescope Science Institute and a member of the National Academy of Sciences, have published their new measurement of the universe's expansion rate. By the light of 6 distant quasars, the cosmological constant was pegged at 73.3 kilometers per second per megaparsec, significantly higher than Planck's prediction. What mattered was how close 73.3 fell to measurements of the Hubble constant by Rees's team, who measured cosmic expansion using a cosmic distance ladder, a method of gauging cosmological distances. The latest measurements in March 2019 pinpointed the Hubble constant at 74.0, well within Planck's error margins. I have never been a fan of dark energy, which is predicted to make up 70% of the universe, while ordinary matter makes up just 5%, which is exceptionally small when this is compared against the 25% of dark matter. I personally believe that the 75% value of dark energy is far too high to contemplate. The volume of normal matter and cold dark matter has a volume of 30 billion light-years of the observable universe. There could be another explanation to explain the enigma of the Hubble constant that does not require so much of dark energy, which is so profound, that it will change how we understand the Big Bang and our universe as it is today. In a universe outside our own cosmos there could be billions of galaxies, and supermassive black holes in every galactic nucleus, surrounded by swarms of stellar black holes. Of great importance is how we understand the size, shape, composition and temperature of the singularity inside the event horizon of black holes. The late Professor Stephen Hawking informed us that there is a link between the mass and temperature of a singularity. A singularity is a location in space-time where the gravitational field of a celestial body is predicted to become infinite by general relativity. The quantities used to measure gravitational field strength are the scale-invariant curvatures of space-time, which includes a measure of the density of matter. Since such quantities become infinite within the singularity, the laws of normal space-time cannot exist. Gravitational singularities are mainly considered in the context of general relativity, where density apparently becomes infinite at the center of a black hole, and within astrophysics and cosmology as the earliest state of the universe during the Big Bang. Physicists are undecided whether the prediction of singularities means that they exist, or existed at the start of the Big Bang, or that current knowledge is insufficient to describe what happens at such extreme densities. A singularity is formed when a star of 8 solar masses has used up and the fusion process stalls when the ion is all that remains to process. Fusion is responsible for the internal pressure of the star, which keeps it inflated, while gravity is pushing down on the star from the outside. When the element ion is all that remains for stellar fuel, the fusion process has great difficulty processing ion, and therefore stalls. The inflation pressure inside the star decreases and gravity wins. The star implodes violently in a supernova explosion, crushing the remains of a star into an object so massive light cannot escape its grasp. Two components may affect the mass of the singularity: the speed of rotation, and the mass of the object when it is formed. The rotational velocity of the singularity may reach the speed of light, 186,000 miles a second, and its mass would then become infinite under Albert Einstein equations of relativity. Alternatively, the remains of the star can be crushed into such a small space that its escape velocity exceeds light speed. Neutron stars are formed when a massive star of about 4.5 solar masses runs out of fuel and collapses. The very central region of the star, the core, collapses, crushing together every proton and electron into a neutron. If the core of the collapsing star is between about 1 and 3 solar masses, these newly created neutrons can stop the collapse, leaving behind a neutron star. Stars with higher masses will continue to collapse into stellar mass black holes. A pulsar is a highly magnetized rotating neutron star or white dwarf that emits a beam of electromagnetic radiation. This radiation can be observed only when the beam of emission is pointing toward Earth, much like a lighthouse, and is responsible for the pulsed appearance of emission. Neutron stars are very dense and have short regular rotational periods. This produces a very precise interval between pulses that ranges from milliseconds to seconds for an individual pulsar. The pulsar inside the Crab Nebula spins 30 times a second. Therefore, a singularity which is smaller than a pulsar should be able to rotate much faster, reaching the speed of light. Theoretically, the temperature of a singularity cannot exceed the Planck temperature. Bear in mind that the Planck temperature is still purely theoretical. We have not seen it, nor are we even sure it exists, and we are not able to create it. The Planck temperature is about 1.416 times 10 square 32 degrees. The Planck temperature limit exists because of something called blackbody radiation. Blackbody radiation is the light given off a body based from its temperature. As an object gets hotter, it releases more energy as radiation than a colder object. In practice, this means that hotter objects will glow bluer, and cooler objects redder. Every object gives off this radiation, which is why infrared cameras work. Humans give off light in the infrared range. So, the temperature of a singularity is over 1,000,000 trillion degrees. At this temperature, a huge number of exotic theoretical atomic particles are created within its plasma. According to M-string theory, there are 11 dimensions, all of which coexist within the singularity as the result of its Planck temperature. I personally believe that the result of all this is that the matter inside a singularity comprises dark matter, which is of extraordinary complexity. Until recently, astrophysicists believed that there was a supermassive black hole in the nucleus of every galaxy in the universe, making the balance of probability of something taking place within a singularity, and causing it to explode, being very low. That changed when a Columbia University-led team of astrophysicists discovered a dozen black holes gathered around Sagittarius A, the supermassive black hole in the center of the Milky Way galaxy. For more than 2 decades, researchers have searched unsuccessfully for evidence to support a theory that thousands of black holes surround supermassive black holes at the center of large galaxies. Columbia astrophysicist Chuck Haley and his colleagues turned to archival data from the Chandra X-ray Observatory to test their technique. They searched for X-ray signatures of black hole low-mass binaries in their inactive state and were able to find 12 within 3 light-years, of Sagittarius A. The researchers then analyzed the properties and spatial distribution of the identified binary systems and extrapolated from their observations that there must be anywhere from 300 to 500 black hole low-mass binaries and about 10,000 isolated black holes in the area surrounding Sagittarius A. Multiply 10,000 black holes by the billions of galaxies in the universe, and you find that the probability of something causing a singularity to explode is far higher. Going back to what I said earlier, in a universe outside our own cosmos there could be billions of galaxies, and supermassive black holes in every galactic nucleus, each surrounded by swarms of stellar black holes. If just one of the singularities exploded, we would have the conditions of the Big Bang, the creation of our universe, a bubble universe coexisting inside a universe outside of our own. The original singularity vanishing along with its event horizon. In fact, there could be 2 or 3 bubble universes, one of which would be our own. The Big Bang theory is the prevailing cosmological model for the observable universe from the earliest known periods through its subsequent large-scale evolution. The model describes how the universe expanded from a very high density and high temperature state, and offers a comprehensive explanation for a broad range of phenomena, including the abundance of light elements, the cosmic microwave background, large-scale structure and Hubble's law. The farther away galaxies are, the faster they are moving away from Earth. If the observed conditions are extrapolated backwards in time using the known laws of physics, The prediction is that just before a period of very high density there was a singularity, which is typically associated with the Big Bang 3.8 billion years ago. I personally believe that at the moment of the Big Bang, inflation was the result of dark matter inside the singularity spewing out under immense pressure, creating our universe in a few minutes. In addition, the 11 dimensions released from the singularity divided into two sets. 4 composing our universe, with 6 others rolling up so small they are much smaller than a typical atom. The fourth dimension is a strange concept. A 4-dimensional space or 4D space is a mathematical extension of the concept of 3-dimensional or 3D space. 3-dimensional space is the simplest possible abstraction of the observation that one only needs 3 numbers, called dimensions, to describe the sizes or locations of objects in the everyday world. For example, the volume of a rectangular box is found by measuring its length, width, and height, often labeled x, y, and z. The geometry of 4-dimensional space is much more complex than that of 3-dimensional space, due to the extra degree of freedom. Today the universe is 13.8 billion years old. There could be billions of galaxies, and supermassive black holes in every galactic nucleus, each surrounded by swarms of stellar black holes. Just as our bubble universe was created inside a much larger cosmos outside of our own universe. If just one of the singularities exploded, once again we would have the conditions of the Big Bang, the creation of a new universe, a bubble universe inside our own universe. The original singularity vanishing with its event horizon along with it. Likewise, there could be 2 or 3 bubble universes inside our own. I propose this theory because it does seem to answer several perplexing questions. What existed before the Big Bang? Answer: a singularity inside of a black hole coexisting within a larger universe outside of our own universe. What is dark matter composed of and why can't we see it directly? Answer: dark matter was created inside our primordial singularity, where the immense Planck temperature, infinite mass, and 11 dimensions coexisted, creating the right conditions for black matter to form. Dark matter is nature's way of hiding each bubble universe that forms, from alien observers looking for them. Why is it so difficult to measure the cosmological constant precisely? Answer: if there are 1 or more bubble universes inside of our own cosmos, each would be expanding at different rates. The inflation pressure alone would cause our universe to expand quicker than it would do normally. Therefore, there is a need to decrease the value of dark energy to take this into account. Where are these bubble universes hiding in our own cosmos, if they exist? Answer: inside the giant voids of empty space as shown by the cosmic background radiation. Astronomers have been studying these voids for more than 5 years, and consider that they may be direct evidence of an outside universe bumping into ours. While voids are theorized to be empty space, it is possible that in fact they house a bubble universe cloaked within a higher dimension. In 2015, astrophysicists discovered a strange barren area of the universe which was much colder than the rest of space and seemed to be missing 10,000 galaxies. The cold spot, which is 1.8 billion light-years across, is the largest known structure ever discovered, yet appeared to contain 20% less matter than it should, and has baffled scientists since it was recorded. Experts at Durham University believe that an outside universe crashed into ours, causing a shunting action much like in a traffic accident when cars pile up on the motorway. The impact was so extreme that it pushed energy out of a huge area of space, creating the cold spot. Scientists now believe that if our universe ballooned up into a vacuum after the Big Bang, then trillions of others could also have formed in the same way, creating a multiverse of other universes beyond our own space-time. My theory of bubble universes coexisting inside bubble universes turns the Durham University's proposal into a two-way proposition. Not only could other universes be bumping into our own, but also bubble universes coexisting inside our own universe could be hidden in the largest voids. While voids are theorized to be empty space, it is possible that in fact they house a bubble universe cloaked within a higher dimension. Dark energy accounts for 75% of our own universe. The universe is all of space and time and their contents, including planets, stars, galaxies, and all other forms of matter and energy. While the spatial size of the entire universe is unknown, it is possible to measure the size of the observable universe, which is currently estimated to be 93 billion light-years in diameter. However, if some dark energy and one or two bubble universes coexist in our universe, it would help explain why our cosmos is expanding 9% faster than predicted. It may sound extreme to introduce bubble universes coexisting in ours and other universes, yet it cannot be ruled out. The whole concept of the multiverse is that of a cosmic foam in hyperspace. This is interesting, when one considers the fabric of our universe also being likened to a cosmic foam. Of course, I could be wrong in my theory, however, it will be very interesting for mathematicians to test the proposal with their equations, to see if it stands up to scrutiny. In conclusion, the multiverse seems to be a cosmic foam, from the very fabric of each universe, to bubble universes coexisting inside one another, forming a cosmic foam in hyperspace. This model is so profound, that if it is accepted, it will change how we understand the Big Bang and our universe as it is today.